I have already started to grade. So I already saw 2 students that got over 90 points. So they did pretty well. But there are some are not good enough. So I plan to propose a way for whoever didn't do well enough to make up. Because we don't have too many scores for exams. If you lose points over here, at the end your overall score could be low. This is 10 points. Yeah, our exams are in total 40 points. So if you only get half of it, then your overall total your maximum is 80. Then if you lose something here and there, you will end up with 60, which is not very good for a graduate program. So I plan to work on the idea of doing a makeup exam. So today I will be making some explanations about the exam. If I don't have your exam sheet, then basically I will stop collecting. So if you don't have a score for the past weekend, then you can use the makeup opportunity to get some score. So what I propose is if you get a score of A, your original score, and if you get 100, then you don't need to do this. Or if you get something like 95, you don't need to. And then so you basically you want to make up for what you lose. So you lost 100 minus A, right? But I cannot. To be fair, if I give you makeup and then you can become higher than who got really high score for the first time, so I propose that whatever you lose, I will multiply by 80%. So basically, you are making up for this score. So for example, you got 30 points for the first time. Then it's 70 times 80%, it's 56. So if you do 100% next time, you get 56. So your total would be the sum of these. So you will get 86, right? So at the end, your final score will be the sum of these two numbers. Okay. So for the makeup exam, I will use the same style. And this weekend. If you keep on doing this, every weekend you are doing an exam. Okay? So I will create a new exam sheet, completely different problem. So now you get a sense what kind of problem I will make. I will make up something that at the first time you will think, oh, what is this? The professor didn't talk about this in the class. So I guess one of the difficulty is that you have no idea what I want you to do. So for some of the sheets, I noticed you started to Google for some references, and then you took it from the reference, but didn't do exactly what I asked you to do. So I will talk about that later on. Is everyone okay with this? Okay, so this weekend I will do this again. And you can join or not, it's up to you. So I will finalize the grading before the weekend, so you will know, okay, if you want it or not. It's okay if you're not doing it, then your score is this. Okay, if you do it, if you already get 95 and you still want to do it, it's up to you. Okay, if you just enjoy doing exams, I don't mind. Yeah. Okay, now, okay. So let's talk about how I arrange the points. This student did a pretty good job. I'm sorry, I'm showing your score. Okay, you are the first person I grade, and you did very well. Okay, so in this sheet, I should show you the other one. So in this sheet, I'm sorry, I will post this on Google later on, because my grading percentage is shown in your solution sheet. So if you write down what I told you to write, then you get 5 points. And for the first problem, you're supposed to do finite difference for derivatives. And if you do that and do it properly, you get 20 points. If you didn't use finite difference, you will lose some points. And it depends on how much I would like to give you. And then once you get all the derivatives like this student did, perfect, and apply everything into the Newton's equation, doing this right, then you got another 5 points. If you do the convergence check properly, 5 points. And you are supposed to iterate until everything converges. So if you iterate properly, you get 10 points. And at the end, you need to claim, what are the answers? You need to claim, okay, this is the final answer. If you answer properly, then this is the another 5 points. So up to now, I think you get 15. For the second problem, very similarly, but for the second problem, you need to do line search. So the distribution changed a little bit. For the finite difference, because you don't need to do as much as the first problem, so only 10% for finite difference. For the line search, if you do it properly, you get 15%, because line search is a special feature inside steepest descent. So I give line search a greater percentage. If you apply the steepest descent equation properly, you get 5%. He did it right. How come there's no equation? Because the equation was shown here. He used it here. So at the end, there is an equation in terms of alpha, unknown alpha, and he plugged it in. So he did it right. And for here, this is for convergence check, 5 points. And you're supposed to iterate And I mentioned you need to stop until k reaches 3, I think. If you iterate based on the rules I mentioned properly, then you get 10 points. So how come he lose some points? He did something I have no idea what he was doing. So this part is weird, okay? So at the end he got 92, a pretty good score, okay? So I will post this on Facebook, so for reference later on, if you check how I grade, I will, if you have issues, you can send me emails, okay? Maybe I didn't grade based on what I said, or when I count the points, I made a mistake on the points, then you can let me know. Okay, so let me show you, since, sorry, Wei Yan, your sheet was shown, so I just use yours as an example. For my grading, I will just do some marks like these, and if there's an issue, I will write it down like this. Okay, you did everything correctly, but you need to converge until k reaches 3. He didn't, his solution process was not finished. He's supposed to do this one more time, because k was 2, I think, or 1. So he was supposed to do this for 1 or 2 more times. I guess up to now he's already tired, so he stopped. That's fine. So for you, if you iterate properly, you get full mark 5%, but I only deduct 3 points because he did iterate for once. So I think he knows how to do it, but he didn't finish. So I will be judging within the range of 5%. I will make a decision. Okay, maybe 2 points off, 1 point off, 3 points off. It's really up to me. Okay, and this part I have no idea what he was doing. So, and he didn't answer. Okay, A star is this, B star is this, C star is this. So that's 5 points off. That's how I grade. Okay, so I will write down the final score. I will sign here. So to show that was done by me, not by my student. Okay, all my students have no access to the exam sheets. So I save everything on my desktop only. So no one can touch it. Okay, to be fair. That's the rule. Okay. Now I'm gonna talk about how this problem can be solved. When I said I complete this within an hour, what does it mean? I program this exam sheet for this take-home exam from scratch. So I time myself. Okay, if I have to do this, I guess some of you may do this as well. So I guess you will need double or triple of time of mine. So if I can do this within 1 hour, then the exam should be able to be done within 2 or 3 hours. That's what I guess. Maybe some of you did for 6 hours, or it took you 2 hours to figure out what the problem was. Anyway, this is what I did. So let's take a look. So just up to this point, data. Okay, there's a bunch of data, experimental data. And there are 2 columns. The first column is different sampling positions of X. And the experiment give you some responses. 6, I just gave random numbers. So 6, -3, 0, 4, and 35. This happens all the time in your own research. You will be sampling some variables, and then you will do some simulations or experiments, and you will get something in return, right? This is what happens when you do research, okay? So I'm trying to use this opportunity for you to learn something new. This is called a least-square approximation. And what happened was, we're trying to find a function that fits these this set of experimental data a best fitting curve. And what I proposed was, let's take a look at it. We can have a polynomial function. Here. We can have here. We can have a polynomial function with unknown coefficients. What are the parameters A, B, and C so that this model fits the experimental data the best? But how do we claim the best? Over here I said we want to minimize the sum of squared errors. Okay? But what does it mean by minimize the sum of squared errors? So over here, I give you a hint. Squared error of the ith experimental data, basically the ith one, for example, the third one. Third one, okay, over here, x equals to 3, f equals to 0. Okay, so can be written as the following. So your function value fi basically is this 0. Xi basically is the ith x. You just plug them in. So 0 minus a times 3 squared minus b times 3 minus c. And then this term basically is the difference between the real number fi, which is 0, and the model. When you plug in x into the function, what you end up with is the model. You basically have your real f minus the approximated f based on the polynomial model. Okay? So this is so-called the ith error. And because the error sometimes could be positive, sometimes could be negative, so we take a square of it so that it's always positive. When you sum these terms up, at the end you have 5 of these terms. They are all in terms of A, B, and C. So you end up with a long function where the A, B, and C are remaining unknown. You just need to make good guess or figure out a way to find what are the best choices of A, B, and C, so this error could be the smallest. That's it. So basically minimize the sum of this term from I equals to 1 to I equals to 5. That's the idea. So over here I wrote the MATLAB code. I have data with the first number, first one here, second one of this one. I just take random numbers. Then I plot out the data. So we can take a look. Basically, in a coordinate, in a figure, you realize it's just like how you are doing in an experiment. You sample x of 1, 2, 3, 4, and 5, and you get responses of 5 different values. And you want a polynomial to fit those 5 points the best. Okay? So that's the idea. Now over here I formulate the function in terms of A, B, and C. So up to here, this is how the function looks like. You notice there are a bunch of square terms. Inside, the only remaining unknowns are the A, B, and C. And the rest are just even numbers that have already been plugged in. Okay, so it's important that you know what you're doing. Okay. Some of you figure out this is the best fitting problem and maybe Google and realize, oh, there's something called least square approximation. And there are easier ways to do this, not by this optimization approach. They even use that easy way to get the solution and use it as the starting point. So that's exactly what I asked you not to do. Over here I said you are not allowed to use a different way to find a solution first. For example, ask ChatGPT or use any best fitting software. Because you actually can do it. If you learn from the internet, they give you an equation and plug in, that's the answer. Okay. So over here, I'm not asking you to use that equation, I'm asking you to solve it iteratively. Okay? So some of you did that, then you will get some points off. Okay? You know, it's very difficult for me to find a proper problem which cannot be well recommended by ChatGPT. So it took me some time to figure out, okay, this could be a problem that maybe ChatGPT won't give you enough. So you still have to put your heart, your mind in it. You still need to think a lot. Okay. Anyway, then the rest are just the same thing based on what I did in the class. So over here, the first part is Newton's method. The second part is steepest descent. So let me just show you the results. So at the end, I actually plot out the best fitting curve. You can see the blue one is the one found by Newton's method, which fits the 5 points better because Newton's method was able to find the optimal solution. But the red one was found by steepest descent, where I stopped at the third iteration, just like what I asked you to do for the exam. So it was not supposed to find a good fit, but you can still see the trend. Okay? And let me show you what will happen if I change a number. Let's say this is 9, let's say this is 1. Okay, so you see different points, different values, and different best fitting. Okay? So the formulated sum of square error will help you to find the best fitting coefficient, and the plot based on the best parameters is supposed to fit the experimental data the best. Okay? If you want to know how I plot those, I will give you this file so you can just play with it in your own time. Okay, so that's my explanation about the exam. Any questions? Yeah.
So when I do this, the same things, actually I change delta several times, but when I increase delta, the steepest descent it will become bigger.
Yes. So delta has to be small, especially for steepest descent. And when you do your exercise, most of the time you will do some round off. You will do some rounding. So if you do round off, those digits in the end is important actually. They matters. If you round off with fewer digits, that means every value you get in the equation is not accurate. You end up with something not accurate enough. So your solution process won't be too precise. And sometimes you even have a diverge process. So steepest descent sometimes diverges when your gradient approximation is not good enough. Also for Newton, I saw one of you did Newton and did some round off. So the Newton was not precise enough, and Newton was supposed to converge at the second iteration, but in his exercise, the solution process converged at the third iteration. I still give a full mark because it's a reasonable process. It really depends on what kind of round off you used, so you will experience different iterative results. And since I'm using MATLAB kept a very long digit behind the dot. So of course computers will do a really, really good job for calculation. But for you, because you are doing some hand exercise and you may use calculators or you may use computers to compute, and you don't want to copy all those digits, sometimes just do round off. And every time you do round off, you will lose a slight bit of accuracy. That's fine. I didn't reduce the point if your process was not accurate enough. You never see that, right? If you, for example, if you do Newton and you keep on, I saw, yeah, you're right. One of you used Newton and he used a terrible round off. So it took him such a long iteration to converge. I think I didn't give points off. I just write it down. I said your round off is making the process so inaccurate. That's why your Newton's methods approach is taking so much time. So, but I think I didn't give the points off anyway. Okay, so that's it for the exam. I hope you guys will do a better job next time, or the makeup exam. To be honest, I don't want to do makeup. I need to use my brain to think about something you cannot just easily get from internet or from ChatGPT. Because you can directly copy my exam to ChatGPT, it may just tell you what to do. So I don't want you just do that, because you will learn very little if you do that. Anyway, I will do as I promised. I will give you a makeup. I hope in the following exams you guys don't need makeup. Everyone get an A or A plus at the end. That's my goal. I don't mind everyone get A or A plus. Okay, so today, we're going to move on to the next gradient-based approach. Oh, do you guys know what this is? This is the exam note I took when I took the optimization course. Those are my notes. Oh, of course, some others are just handouts from the professor. Oh, and sometimes I even have my seniors' copies. I use it to prepare for my qualified exam. So I think this much is my notes for the course. Oh, also here. I got an 84 for the midterm. Yeah, so so what is this? This is the second time I took the course. Why did I took the course multiple times? Because my advisor asked me to take it again, kept a series of notes, and then transfer them into Word documents. So in the future, he can publish a book. So I took the course 2 times, or maybe 3 times, I don't remember. And every time I take a course, I take handwriting notes, I just seal them as a book. So in my lab, I have a bunch of this kind of books. I just want to encourage you to keep all of your notes, okay? Because this was 2007, I think. It's already almost 20 years ago. You may use it in the future in your career, right? You may become a professor. when did I know that I want to become a professor? When I was a master's student, I didn't know I would study for PhD. I just enjoy doing research. And I know I can do better than my lab mates. I know I'm the best student in the lab. So I realized I should study for PhD because I feel like I can do even better. But at the time, I didn't know, should I become a professor or just work in USA? I know whatever I do, I need a PhD degree. So I decided to just go for it. At the time, I applied, I studied at Rutgers. Rutgers is a university in New Jersey. It's a state university. It's a good university. The USA ranking is ranking from 30 to 40, top 30 to 40. Right now maybe 50, a little bit dropped. But still, top 100 university. But it's not something like a top 20 or top 10. So I always wanted to do research in top 20 universities, get a feeling about how they do research. Because if you are not there, you never know how hard they work. So when I graduated as a master, I applied for MIT, Princeton, Carnegie Mellon, all rejected. So all got rejection, okay? And before I got the rejection, I even sent emails to some professors over there and say, hey, can I stop by your office and then tell you what I'm doing? I'm so interested in your research on specific topics. Can I work with you as a PhD? Something like that. I even drove for 8 hours from New Jersey to Pittsburgh. It was a long drive in order to meet one professor in the university called Carnegie Mellon. It's a really, really good, it's like a top 10 university. The professor agreed to accept me, but he said he has no funding. If you pay for yourself, I accept you. But that's too much. It's like more than 1 million Taiwanese dollars a year. It's too much. So if I have a rich father, then I probably can stay in Carnegie Mellon. And he said, even your family is rich, I don't want it. I want industrial investment. Because that's a good investment for his lab. He doesn't want my family's money. He wants industry money. So if you can find some industry to invest you, I accept you. That's the deal. I couldn't. I was a master's student. How could I do this? If I can, then I just go for work. So at the time, I didn't get my opportunity to study in other places. I stayed at Rutgers, and I started to work on optimization. And I didn't force myself to industry or academia. I just know I just do a good job and then graduate. Once I graduate, I know I can apply for professor. I can apply for industry. I decided to just try all those and see which one fits me the best. So at the end, I become a professor. So that's my story. I hope that makes your life better. Because sometimes, good stories can inspire you. I hope my story can inspire you. Okay. I need to find the notes about conjugate gradient. Let's see which one is better. Okay, so today I'm going to talk about a method called conjugate gradient. The derivation is long, and it's quite boring. At the end, you will end up with an equation and a solution process. If you have no idea what I did for today, that's fine. You just need to know how to use it. Okay. So, conjugate gradient. So why do we have this method? It's a method that only uses the gradient, not using Hessian. So just like steepness descent, but has the ability to update gradient information. Actually, it's like a direction based on some kind of derivation from, I should not say from, I should say based on, another based on, with patient. So there's a unique way of updating the gradient, and the way this method update the gradient was derived from something, a long derivation where Hessian exists. But they figure out a way to remove it. So later on, we don't need to truly compute for Hessian, but it has a little accurate, it has some good accuracy similar to Hessian. So this is a really powerful method. You don't really need to compute Hessian, but you have good accuracy on the direction, moving direction. Okay. Before we start, we need to know something called the conjugate directions. Okay, so what is it? So we're going to provide you a symmetric matrix, so-called a Q matrix, and also two vectors. Over here, I'm gonna name them as D1 and D2. Okay, and they are Q orthogonal. But what is Q orthogonal? In other words, conjugated with respect to Q, if what is satisfied. If D1 dot Q dot D2 equals to 0. Or, if you don't like to see dot products, you like to see vector and matrix multiplication, then D1 transpose Q multiplying D2 equals to 0. If you like it in this way, they are the same. So what does this whole thing mean? If you have two different vectors in the space, and if you have a symmetric matrix called Q, when you have D1 dot Q dot D2 equals to 0, then you can say these two vectors are Q orthogonal. Okay, so what does it really mean? Whenever you have something like this, a matrix multiplying a vector. It's just like applying a transformation matrix on top of a vector. So you are applying some kind of Q transform onto D. So it's like after the transformation, originally you have a D1 and a D2. The D2 is being transformed to a newer place. After the transformation, they become orthogonal. So earlier, probably they are not orthogonal, not perpendicular, but after the D2 was being transformed by this Q matrix, they become orthogonal. So we call these two are Q orthogonal. Okay, so why do we do this? From last time, did you notice something? The steepest descent is trying to move toward a newer position that is orthogonal to the earlier position. So it's trying to move along this 90-degree direction. But if your 90-degree direction is directly pointing to the minimum position, then your optimization process could be faster, right? So what if I'm solving a problem like this? What if I'm doing something like this? Then when you draw the contour, they are circles. They are circular contours. And if you use steepest descent, let's say this is your initial gas. And from the gradient direction, it's steepest descent direction, basically the negative gradient direction. Negative gradient direction. It's actually pointing to the center, right? So if I use steepest descent to solve this problem, it's going to be so fast because the direction is right. But when I solve a different problem like this, it's a different story. Let me see which 10, 1. Okay, so I think it's going to look like this, right? I'm not sure. If I plug in 1, 1 here, that's 100. 1, 1 here, that's 11. So if I have 0, 0 and 1, 10, 0. Oh no, the other way. The other way. So it should be, the contour should look like this. Is it?
Yes.
Just I want to double check. I don't want to make a mistake here. Just let me double check with MATLAB. Easy contour x1 squared plus 10 times x2 squared. No, it was the early one. Sorry. So the first one was right. Okay, so get back to MATLAB. I'll get back to iPad. It was the first one. Okay, so when you have a function like this, when you have an initial gas, the gradient direction is the perpendicular direction against the contour, so you will be moving straight but not pointing to the minimum point. So you will be doing this zigzagging thing, like what I showed you last time. You will be doing this 90-degree turns. So what if you can transform this elliptical space to a circular space, then you will be doing what's on the left. So the idea of Q orthogonal basically is trying to transform a elliptical space to a circular space, so that when you apply so-called the gradient, then you will try to point to the minimum point. Okay, that's the concept. But later on, when we do derivation, you probably won't see this kind of concept anymore. It's all about math, nothing graphical. Anyway, so if you are curious about what's gonna happen, let's start to look at this. Okay, let me see if I need this. Okay, we will do that when we do. Okay, so now start the derivation. Let's say we are minimizing some kind of function f, and it could be any function. So far, for any method that we work on, what we do is to approximate it as a second order polynomial. So what we can do is we can approximate it by a polynomial. So over here, I'm gonna write things in a simpler way so that our derivation won't be too long. So for now, I'm gonna say k like this, and I will tell you what is fk. If it's a vector, I will keep the vector sign. If it's a matrix, I will keep the sign at the bottom as well, so you know whether it's a vector or not. But remember, for gradient, you don't need to have a vector sign anymore. Gradient itself is a vector. Okay? So what does that k mean? Fk equals to, okay, just plug in the k variable. And of course, we define xk as a simpler version, just a lowercase k, no more uppercase bracket k. Okay, and similar for gradient fk and Asian k. Okay, just the k represent plugging in the k variable. So over here, so I'm gonna do something a little bit right here. I'm gonna name this approximated function as f, I don't know how to pronounce it, f hat. Okay? So just call this function as a f, whatever it comes up. So let's take the derivative. If I take the derivative because we have multiple variables. So when you do first order derivative, it's actually taking a gradient. So this is taking derivative, basically applying the gradient. Okay? So when you do that, what you have at the end, this is just a constant, right? Just a constant number. So when you take a derivative, it disappears. And this is also a constant. Haitian is a constant, basically a matrix of values. So the variables is where? Oh, this is a constant as well. This is basically the k variable, k position. But this is the variable. X is here. So over here, this is the first order term. This is the second order term. So it's like an ax plus bx squared. So when you do take derivative at the end, what you will get is the coefficient right here. Because the first term has an x. When you take a derivative, x disappears. What's left is coefficient. And for the later part, you have two brackets of x minus k. So it's like a x minus k squared. So when you take derivative, you have a 2, and then multiplying the 1/2 in the front. So the coefficient disappears. At the end, it's gonna be this. Okay? That's what happened after you take the derivative. I'm going to call this equation 1. Later on, we may use it. Now, okay, so that's the first step. Next, we want to define an equation. It's xk plus 1 equals to xk plus alpha k and dk. So what is this? This is what we saw in the steepest descent method. This is basically the step size, and this is like the moving direction. Okay? And for steepest descent, we basically move toward the negative gradient direction. But for conjugate gradient, we try to figure out what is the best direction to move toward. Okay? So if we have this equation, we can rewrite this equation as the following. We can we can have equation 2 and then plug in. Let me see, how do we plug in? Okay, I think we will figure out this equation later on. We need this one. Let's see. How do we derive the Okay, so for steep is decent. We know dk equals to negative gradient direction, right? This is what we always did for steep is decent. So for conjugate gradient, we want to do something else. Conjugate gradient. So over here, we are going to add a new term on top of the steepest descent. So we're going to do the same thing, but we're going to add a new term, so-called the beta k minus 1 and dk minus 1. Over here, d is vector. I forget to put the vector sign. D is a vector. D is a vector. So here I introduce a new term. What's inside the new term? Basically, beta is some coefficient for k minus 1 iteration, and this is the moving direction of the k minus 1 iteration. So we just want to use the moving direction from the last iteration, and we apply a coefficient in front of it, like a pre-multiplier. But so far, this one is unknown. We have no idea what beta is. But we pre-multiply the previous moving direction, and then we sum it with the dk, the steepest descent direction that we know. So it will be a directional update on what you usually do. So usually you will move along the steepest descent direction, but right now you will be shifting your direction by some update, beta dk minus 1. So over here, we're going to figure out what is beta k minus 1. Then the job is done. And can we figure out a good way to compute beta so that it's moving toward the minimum point? Okay, so we are going to call this equation 3. So far, we have equations 1, 2, and 3. So at this point, there are still some unknowns. If we know them, we are done. We have no idea what is the step size. We have no idea what is this beta coefficient. Okay? Now, over here, we are actually going to do so-called a Q. We assume two different vectors are so-called a Q orthogonal. We're going to assume which two vectors? The current moving direction and the previous moving direction are Q orthogonal. But what is Q? We don't have a Q here. In our derivation right here, there's only one matrix. It's actually the Hessian. So we just assume they are so-called the Hessian K orthogonal. Let's see if that works. We can do that. We just decide to have two moving directions, and we want them to stay HK orthogonal. That means later on, I can apply HK on each one of them, so that particular one will be transformed to some a newer space, and the original one of it and the transform one will become orthogonal. And the way I'm gonna transform it is gonna be based on the Hessian HK. Okay, so if you are happy with what I assume, then you must agree dk dot product Hessian k dot product dk minus 1 now equals to 0. Because that's the equation you must satisfy if you assume two vectors are some matrix orthogonal. If that is true, then you have this equation. Okay, so I'm gonna call this equation 4. And if this satisfies, we call the dk and the dk minus 1, they are conjugated. They are conjugate with each other. So we that's why we call this as a conjugate gradient method. So we sometimes just say dk is conjugate to dk minus 1. Which sometimes we can say this sentence. Okay? So they are, coupling such a way. And the way they are coupled with each other is based on this exact equation number 4. Okay. If you're okay right now, then of course you have no idea what's gonna happen. When I was a student, I just tried to follow what my professor was doing. At this point, I have no idea what happened. Okay. So all you have to do is just keep on watching, like watching a movie without knowing the ending, and you will know it whenever it's finished. Now, we are going to do something. Let's see. I need to figure out one equation. dk times gradient. Let's see how we get this. Oh, okay. Okay, I know what's going on. So over here, we are going to from here. Let me call this equation 0. Okay, equation 0. So from equation 0, here, the very first one, from 0. So I'm gonna copy the whole thing. Copy. And then paste it here. But this time, I'm going to do something with it. Okay, over here I'm going to, I don't need this anymore. I'm going to directly plug in the k plus 1 variable. So over here, This is k plus 1. So this becomes the equation of k plus 1, right? Just plug in. Okay, just plug in kx of k plus 1. Once you do that, you are going to take derivatives. Let's see. Just if I take derivatives, I will get this one, k plus 1, and then dk. That one is alpha dk. Trying to figure out one thing. How come I have this term? Let me check the other notes. Okay. Over here. Okay. The other note, tell me why. Good. So after that, you are going to plug in something. We're going to use the one with alpha. Okay, so use equation 2 and plug in the newer equation. So plug in 2 to the equation on top. So what you will get is the same thing here. What is equation 2? Equation 2 is xk minus xk plus 1 minus sk equals to alpha k dk. Okay, alpha k dk. So over here, this term, and this term, they are replaced by alpha k dk based on equation 2. So I'm just going to write down them. Alpha k dk. Over here, you are going to have 2 alphas. They are just scalars, so you can put a square here. And then dk. Dot product with Asian, dot product with another dk. Right? Great. After plug-in. Now, for all the methods that we introduced, just like Newton's method, we want the derivative of this quick equation equals to 0. So we want derivative of this equals to 0, so that just like Newton's method, this idea help us to find the extreme point. So let's just take a derivative. But when you do that, you notice the only unknown will be alpha k, because the rest are just values, right? So you can take a derivative with respect to alpha k. So when you do that, what's left would be dk dot product gradient f plus alpha k times dk dot Asian k dot dk. That's what's left. And you want this to be 0. Okay. So from here you can take out the pre-multiplier, which is dk, and what's left on the right will be gradient f plus alpha k, and then Asian k dot product dk, and this equals to 0, right? And over here, what are we going to do? We are, from some equation we know from which one? Okay. If you check, that was alpha. Where did I get it? Equation 6. We didn't do. We need this one. How do we do this one? 1 and 2. We forget to derive one equation, which is having 1 and 2 together. So let me took 1 and 2. Okay, so since 1 and 2 tell us paste, this is 1 and 2, and I'm gonna erase some of the stuff here, and move them together. This is 1 and 2. So when you put 1 and 2 together, you can have delta f k plus 1 equals to fk plus hk dot product xk plus 1 minus sk, right? You just plug in k plus 1 into the first equation. And over here, you noticed equation 2 tell you this term is basically alpha k dk. So at the end, you have gradient fk plus alpha k dk, right? And you realize this guy is the same as this guy. So what we derived earlier can be rewritten as delta k plus 1. So dk times gradient f k plus 1 equals to 0. So from what we should have derived earlier. So we got a new equation, dk dot product with gradient f k plus 1 equals to 0. This is going to be my equation 5. How many equations are there going to be? Another one. Okay, so great. We have equation 5. And this one, I'm going to call this one equation 6. Okay? That one is going to be useful as well. And did we do this already? Yes, that one equals to 0. Good. Now, we had many already. So earlier we had this third equation. It's some equation we defined, and this equation is supposed to be general enough. The third equation. So we can also so it's general enough for all the iteration number k. So what if when we advance our k by 1, this equation is still valid? So over here we also want to have a dk plus 1. How is this one going to look like? We also need it. So like I said, this is like a movie. Okay. So I'm just advancing all the k's by 1. This one has to be valid. Even if we advance our third equation by even if we advance our index by 1 in the third equation, this equation is going to be valid. So I'm gonna call this one 3 prime. Okay, it's like a brother of 3. So we need to do something with the 3 prime. So I'm gonna copy this to somewhere at the bottom so I can use it. So from the 3 prime, okay. Okay. I have no idea how mathematicians come up with this. I am not the one who did it. Okay. All I can do is follow and then just replay the movie for you. So I'm gonna post multiply. I'm gonna post multiply k dot dk to the third 3 prime equation. So what you will have at the end would be dk plus 1 post multiply k and dk. Okay? So basically do this for the right hand side. What you will get at the end would be just do the same thing for all terms. Right? Okay. And when you do this, you realize, what is this? This is basically the definition of Haitian K orthogonal. We assume all the dk's, dk and dk minus 1, dk and dk plus 1, they are so-called HK orthogonal, right? So what's the definition of HK orthogonal? When you have DHD equals to 0. So this one is 0 because of HK orthogonal. Okay? Like how we yeah. If the equation 4 is valid, you just advance all the index by, here is k minus 1. Then it's a little different. Let me think about it. If you advance this by, let me see. It is a little different. Can we do this? If you advance by 1, then it's different. Because we only said the dk is orthogonal. Do we assume in a different way? Let me see. Do we use this all the time? Let me see about the other note. Which one is right? Over here is minus 1. So how about the derivation? I question myself. I question the note. So I'm just going to put a question mark here. Later on, I can come back and see if maybe my note was wrong. So shouldn't this be k plus 1 here? Just a question mark. And shouldn't this be here and here? Because I'm not trusting my notes at this point. But if this pink mark is right, then what I'm writing here equals to 0, right? So that, if at the end that equation over there was never touched, then that means my notes should change it to plus 1. Okay. Yeah, let's see. So let's assume we're using the definition of pink, the pink marks. Then I feel like only if the pink marks are right, then this one equals to 0. Otherwise, I cannot convince myself. So what next? So if the left-hand side is 0, then we can work on the right-hand side, and we notice that here are a bunch of known values, known information multiplying with each other, and these are some known values, right? Everything with a k is known. So at the end, you can actually derive what is beta k, right? So beta k is gonna be right here. Over so if you minus the index by 1, you have the beta k minus 1. If you have beta k minus 1, earlier we said we have no idea what is beta k. Just throw it over there. You can do it. You can have so-called the conjugate gradient approach. And how about alpha k? Just do line search. So up to now, you can already do conjugate gradient approach. So it's a gradient update approach with some kind of beta premultiplier on previous moving direction, and the beta k minus 1 information has the knowledge of Hessian. But if you do this using the equation right here, you're still using Hessian. So it's basically like Newton's map. Then why bother? Just use Newton. So the goal is to replace the upper part and the lower part inside beta by different terms, so that when you evaluate beta, you don't need to compute for Hessian. So what's next is that we are going to replace the terms inside beta so that we don't see Hessian anymore. Okay. I'm going to call this, somehow in my notes, it's equation 9. Where is 7 and 8? I have no idea. Oh, it's on the, I'm gonna call this 9 because what happened was, later on I have 7 and 8, and then my professor realized, oh, we need to call this 9, otherwise we cannot use it. So, just to be consistent with my notes, I'm not gonna call this, I'm going to have jumping numbers. It doesn't matter. Now, okay. What do we do now? How do you call the upper part? Denominator and nominator. Which one is the upper one? Which one is denominator? Which one is denominator? I forget. I'm gonna call it upper and lower. Okay. I'm not good in Chinese and not good in English. Okay. So the upper part in beta k equals to what? Yes. The gradient f, k plus 1, also Hessian, and also dk. How can we remove the hk? So we're going to plug in several equations and then try to remove hk. So what we're going to use now is going to be the equation 2 over there on the top. So from equation 2, I'm gonna copy this guy to the side so you can. Okay, so this is from equation 2. Okay, so we can rewrite this guy as we're going to use what we have here. So this would be x k plus 1 minus xk divided by alpha k. Right? We can do that. Now, for the Hessian, we're going to use equation 1. Equation 1 right here. So equation 1, copy, and then paste it here. Equation 1 is okay. Because of this equation, okay, so I can do something with So take a look at what you have right here. This is basically what you have right here. Right? They're the same. Because of course, when you apply equation 1, you need to plug in the k plus 1. So they're the same. Then you can rewrite this as gradient f k plus 1 minus delta gradient f k, and then divided by alpha k, right? You can do that. Now let's reorganize everything. You will have gradient f k plus 1 dot product gradient f k plus 1 minus gradient f k plus 1 dot product gradient f k divided by alpha k. Did you realize that we had a term that is given in terms of hk? Now it's completely replaced by a new term where you don't see hk anymore, just by plugging in several different equations over here. So I'm going to call this equation 7. Okay? This is the exact same thing as the upper part of beta k in equation 9. You can use equation 7 instead of the original term in the upper part of equation 9. You can use this one. Then you already replace one of the hk. But we still have another hk at the bottom of beta k. So we need to work on it. Now, we're going to work on the lower part in beta k. So the lower part, no, not yet, sorry. Not simplified enough. So over here, we're going to work on the second term right here. We can do something with it, so our life becomes easier. So over here, we're going to take a look at the second term. So what we are going to do, this can be rewritten as something. Start with let's use equation 3. Equation 3 is here, all the way at the top. Do we use equation 3 or 3 prime? We use 3. So let's get equation 3 right here. Copy it, paste it here, take it, clean this, draw a bracket. Because of this, so we can have, see, we have this gradient fk. So this can be rewritten as negative dk plus beta k minus 1 dk minus 1. Okay, we can do that. And we are going to expand the terms. So negative gradient fk plus 1 dot dk plus negative gradient fk plus 1. Oh, we have a beta right there. Beta k minus 1, dot product dk minus 1. Okay? So over here, dk dot product with gradient fk plus 1. We saw that earlier. dk, equation 5. Equation 5, right here. dk dot product with gradient fk plus 1. That one equals to 0. So dk dot product with a gradient fk plus 1. This one equals to 0 because of equation 5. We can go back and check. So the upper part was, so we call this guy equation 8. Yeah. Now, what do we do? Oh, we're going to deal with the first term of 7. So we're going to deal with 7. We're going to do something with 7 as well. In order to do that, we need to check. So let me draw some arrows so that you know why we're doing this. So over here for the second term, we did the following derivation. For the first term, we're going to do the following derivation. So for the first term, we're going to use equation 6. So equation 6 is here. Let me just copy the whole thing. Copy. And then paste it here. Get rid of the middle one. Delete. Okay, this is the equation 6. Okay. So from here, in order to work with the first term, the yellow marked first term in equation 7, we're going to pre-multiply or pre-multiply? Are we pre-multiplying? Post-multiply. So we're going to, oh, hold on. Why do we do this? Let me see what's going on. Oh. Trying to figure out why we're doing this. This is good. This is good. So we put it back. Man, it's really confusing. Wow. Forget why I do this. understand my own notes. I have to check the other time. Okay, we have this, yes. Second term. Yes, this guy equals to 0. Oh, we need to do further. We need to, what do we do? Oh, so we are going to plug in. So we are not yet, we're not yet dealing with the first term. We are using equation 6 because we want to plug in right here. Okay, we want to plug in. Okay, so we are still working on the second term. So after we plug in, what you get at the end will be alpha k minus 1, plug in, gradient of k plus alpha k, Hessian k dot dk, and then dot product with dk minus 1. Okay, so then we will have, we just expand everything, beta k minus 1, gradient fk, dot product with ek minus 1, plus alpha k, beta k, Asian O. Over here, you have to, when you have something like this, you end up with dk dot product Asian k dot product dk minus 1. Yes. That's another proof. But I'm going to skip it. How come this dot product with this ends up with this? That's another proof. Okay. Because of the transpose thing. But at the end, I'm not going to prove it right here, but you can try it. At the end, you have something like this. So, if you have something like this, let's take a look at this term and this term and see what's going on. From equation 5, equation 5 said dk dot product with gradient f k plus 1 equals to 0. This is what equation 5 tells us. So if you divide the index by 1, then dk minus 1 dot product with fk equals to 0. So that's exactly this term. So this is 0. Okay? And this is happening. This is 0 because of hk orthogonal. But when we say this is hk orthogonal, we were using the blue one. So the pink one, so the original node is right. But how come we can do this? How come we can do this? Here. dk so when we are hk orthogonal with k minus 1, we are also hk orthogonal with k plus 1. That's the only explanation. Otherwise, how can you use it? Okay, so I think, is it right? If we So over here, I'm adding one term. I think we also need dk to be hk orthogonal with dk plus 1. So dk dot product hk dot product dk plus 1 equals to 0 as well. So I'm going to call this 4 prime. If that's the case, then this is because of 4 prime. Right? And over here, this is because of equation 4. Okay. Now, we just eliminate the entire pink term in 7. Because at the end, everything becomes 0. So we can rewrite. We can get back to equation 9. Now our upper part of beta k becomes a simpler term, which can just plug back. Which one? This one back to this one. Okay? So plug back 7 to 9. 7 back to 9. We have beta k now equals to the upper part upper part, which is gradient f k plus 1 dot product with gradient f k plus 1, and at the bottom we have a alpha k, and we also have what's originally at the lower part of beta k, which is dk dot product Hessian k dot product dk. We haven't resolved the bottom part yet. I'm gonna call this equation 10. If we can rewrite the bottom part into a different form, which doesn't have Hessian, then we're done. We already worked so hard to eliminate the Hessian term at the upper part, but we still have Hessian term at the lower part. So now we are going to work on the lower part. Work on the lower part of beta k in equation 10. So it's going to be alpha k dk dot Hessian k dot dk. So for this one, we are going to play with, let me move this guy to here. In order to do this, we are going to recall the equation 6. Equation 6 again. I think we did that earlier. Where is the 6? Here, we have a 6 right here. Oh, we never use it. Did we? Oh, we did. But we're going to use it again. Equation 6 again. So from equation 6 again, and we're going to pre-multiply this time. Pre-multiply a dk term to 6. So what you will get at the end is gonna be dk dot gradient f k plus 1 equals to dk dot gradient f k plus alpha k dk dot Haitian k dot dk. You notice that this is exactly what you have for the equation 10. So in this case, equation 10 can be replaced by what? By, maybe I write it down somewhere at the bottom. So equation 10, what you have earlier becomes, this becomes dk k plus 1 minus dk and fk, right? And again, dk dot product with using equation 5, dk dot product with gradient k plus 1, this is 0 because of equation 5. So at the end, you have something like this. So if you put it back to the beta equation, so your beta now becomes a cleaner version. Gradient fk plus 1 dot product with gradient fk plus 1. And then negative dk dot gradient fk. So there's no more Haitian in the term. Okay? But what you can do is to, sorry, let me get rid of this. We don't plug in yet. We can make it better than, it's even better. So then let me delete this one. We want to deal with this further, then we can have an even greater form. So what we can do is, I'm going to call this one 11. This is 11. So 11 can be rewritten if we replace dk. So where do we have dk? We have equation 3. Equation 3 dk. It's right here. Okay, here is equation 3. Copy it. Yeah. Use equation 3. So plug here. So use equation 3. Plug in. So your equation 11 becomes negative gradient k plus beta k minus 1 dk minus 1, right? Multiply with gradient f. So expand the whole thing, gradient f, dot product with gradient f. We're almost done. Minus beta k minus 1 dk minus 1 dot gradient fk. Again, from equation 5, dk minus 1 dot gradient fk equals to 0. dk minus 1 dot gradient fk equals to 0. This is because of equation 5. At the end, the lower part of beta becomes such a clean version. So in the end, beta k equals to, we have the final form. Gradient f k plus 1 dot gradient f k plus 1. The bottom is gradient f k dot gradient f k. Final form. Final form. So what is beta k minus 1? So just divide all the index by 1. So what is going to be my dk? dk, at the very beginning, equation 5, dk. Copy the whole thing, paste it here. Oh, right? Paste it here, okay. Erase of this, and then move. So we initially said we want a pre-multiplier of beta k minus 1 in front of dk minus 1. We want to update the kth moving direction by the previous moving direction with a pre-multiplier of beta k minus 1. We took more than 1 hour to derive this, and I need to check 2 notebooks to realize, okay, this is the result. At the end, the final equation. Oh, wrong. Minus. So in conjugate gradient, when you have a previous moving direction and you try to evaluate the current direction, you first have negative gradient as well, but you want to plus a previous moving direction pre-multiplied with some coefficient called beta k minus 1. And how do you evaluate beta k minus 1? By this ratio. And what is this ratio? You can also rewrite as the 2 norm of square of 2 norm, right? It's the same thing. Either you inside the MATLAB you can a dot a equals to the length squared, right? So you can do this. It's the same thing. Yeah. Now let's write down the solution procedure of conjugate gradient. If you have no idea what happened and you realize, okay, I watch a movie, I have no idea what happened, but at least you need to know the ending. Solution process. Now, initially, you should have initial gas. Starts with a iteration number k equals to 0. And you need to evaluate your gradient f k. You need this only. You don't need anything else. So, the following will be interesting. If you start with k equals to 0, then if you plug in conjugate gradients equation, there is no such a term of k 0 minus 1, right? You don't have gradient f of negative 1. So initially, in the first iteration, you cannot use conjugate gradient equation because there's no previous time. So initially, solve just like this DC. So you are going to do this. Here I'm going to say dk instead of negative gradient k, where dk equals to negative gradient of if if k equals to 0. Then, starting from the next iteration, we're going to do plus which one? The current. Previous one. So over here, we're going to do this. Okay, you formulate this equation. However, you still have unknown alpha. So in fact, you need to move on to a subproblem to find the optimal alpha. And then, so also for line search, you still need to do line search. And then you are going to update alpha k. Then you do your convergence check. If yes, converged, your optimal would be the last one you had. If no, if not yet, then you move on back to this step, advance k by 1, if this is not yet converged. So for steepest descent, you still need to do line search. Okay. What time is it? Okay. I will give you some time to copy. I will try to program in MATLAB, and then we will finish today. Okay, let's try this in MATLAB, and then we are done. Earlier, I had this for the exam. I'm gonna save this as. Oh, I need to let me just save this for. Do I use this instead? No. Let me just use. Let me use my earlier code. Earlier I had the steepest descent code. I'm gonna save this as a conjugate gradient. So I will remove the lines for Newton. I don't need the lines for Newton anymore. Yeah, and then I'm gonna expand this one into conjugate gradient. So for conjugate gradient, if I still use finite difference, before over here, earlier, it's a negative alpha times gradient, but we For the first run, this is all right, but starting from the second iteration, we don't do negative gradient. We have extra terms. So over here, over here I need to use conjugate gradient. Okay? So the goal is to replace this line. I need to say if my iteration number, did I use k? If k equals to 1, then I will say direction equals to negative gradient, because that's what that's what steepest descent do, right? So over here, I'm just plus a times direction. But when we have, starting from the next iteration, I need to move along a newer direction. So I need to keep, I have to memorize what was my earlier moving direction. So over here, I'm gonna have a memory grade old equals to grade. dir old equals to dir. So after I compute everything, there's an old direction and an old gradient. So in the next run, my new direction will be equals to negative gradient again, plus norm of current gradient divided by norm of previous gradient, so gradient old. And of course, square of them. So you can take the whole thing and square it, that's fine. It's the same thing. Multiplying the old gradient. So this line basically is conjugate gradient. You said to build up this equation, and A is still my alpha. Whatever we have at the bottom basically is the same. And here you have to say plus, and here say dir. I think that's everything I need to do. Okay, let's take a look. What happened? Oh, I had a pause. So, did I had a poor? Maybe my delta was small. Because I was using finite difference. For some reason, the problem I had, finite difference did pretty bad.
Professor,
yeah.
I think you have to multiply the old direction, not the old gradient.
Oh, yeah, you're right. Direction. Oh, thank you. Thank you so much. Let's see if he's doing better. Thank you so much. Oh, yes. Perfect. Now converge in 3 iterations. Okay, it's basically the same point. You cannot tell. Let's compare with the conjugate gradient, steepest descent, and try to see the difference. Maybe I write a new code. And And then maybe I just claim my problems here. Oh, this is the example. So I claim my problems here. Okay. I need to symbolic this here. Let me do this. And I'm gonna just call this a main function. Main optimization. I'm going to write the main code. So later on I can directly call all these. So I'm gonna comment this and change this into a function. Do I return any numbers? I will return x equals to conjugate, and the input will be my f and my initial guess. I'm gonna call this x0. Okay, I'm rewriting this as a function. So over here, I'm gonna comment this because I have my f. I'm gonna comment this because it's gonna be symbolic all the way. My x0, so I'm gonna call this x0 and comment this. And maybe I use the same delta. So I'm gonna just say this. And my delta. So my delta is this. So over here I don't use this line. Yeah. The rest will be the same. But I need a return. I didn't define the return yet. So let me just call this x star in case. So x star is gonna be my last one. So capital X K. That will be my output. Okay. And if I do the same thing for my Newton's code and steepest descent code, we can compare all these. So let me rewrite just like what I did. Over here, steepest descent. So I'm gonna call this steepest. I don't need this line, no sync, no this. And this gonna be equal to K0. Yes, I don't need the delta. So I need to define what is a x star at the bottom. Okay, so for the Newton, same thing, I'm gonna, because I was calling this steepest 2D, so it has to be the same name. And over here, Newton 3D, it has to be called Newton 3D. And, but in fact, I was solving a 2D problem. So I'm just using this as a general code. I don't need this. This is gonna be x0. I don't need this. I forget to throw the delta in. Delta and delta. So, and I need the final line for x star. What else? Over here, I should use final difference. Did I use final difference over here? This is my 3D code. Did I have a 2D Newton? Oh, I have a 2D Newton code. So I should, I don't want to ruin this one. So go back to original, okay? Let's use the new 2D Newton because all the other examples are in 2D. So this one, Newton 2D, not this, this. This guy equals to 0, and no need delta, finite difference, all these are finite difference, and the optimal variable here, copy to here. So I just create functions of all three methods. So first one, use a Newton 2D. Second one, steepest 2D. And I'm gonna, for response, I'm gonna call this x1, x2, and x3. Now for plotting, over here, this is my x0. Okay. Del, okay. For plotting, whenever I plot, let me add a plot ID, okay? So I'm gonna call this figure plot ID. Then they will be plotted in different figures. Plot ID, and then here. So I'm just figure 1, figure 2, and figure 3. Okay, run the code. Oh, I think I don't need the pause anymore. I should get rid of the pause. No more pause. Okay. Otherwise, too many pause. Okay, now run the main code again. So conjugate gradient, Newton's method, 2 iterations. Steepest descent took 6 iterations. And conjugate gradient, 3 iterations. Okay? And let's take a look at the differences. For Newton's method, it's like all the way straight to the bottom. Because Bayesian is perfect for transforming elliptical shape into circular shape, and then you can move toward the minimum direction. So actually Bayesian shows you where the bottom is. Now, for steepest descent, if we take a look closely, you can see it's always taking those 90-degree turns, a lot of 90-degree turns. No more, okay? So if we take a look at conjugate gradient, this one is not 90 degree. It changed a little bit. It changed a little bit. So if we plot figure, oh, we can do this. I think we can just, no, we can't. If we plot figure 3 on top of figure 2, then we can see the slight angular difference. But if we want to do that, I need to claim this is figure 2 as well. But when we do that, is there any should be fine because I use hold down all the time. So I can just run the code. Sorry, run this one. Yeah, so now if we zoom in, the upper line was CP's descent. It will be moving toward this zigzagging. We will be doing this zigzagging approach. But the bottom one is the conjugate gradient. You can tell from the second iteration, it shifted the moving direction by a tiny bit. And that direction allows conjugate gradient to move toward the bottom all the way. So now let's compare how many times we evaluate the functions. I need to, whenever I say subs f, that means there's a function count. So I am going to say fc as function call. Initially, fc equals to 0. Whenever I say subs, my fc equals to fc plus 1. Okay? So it's very easy to evaluate how many times you evaluate a function. Just add this line right after you plug it in, plug in the number. So there's no more plug in right here. You can even plot out the function calls during every iteration. So you can right here say, everyone equals to this, bracket function call equals to number to string fc. Right? Yeah. I'm gonna do the same for steepest descent. So function call equals to 0 at the beginning. And then I add a line of function call plus 1 for every time I say subs. Here, here, here. For the line search, you also substitute into the function, do you? Yes, you do. You evaluate the function several times. That's every time you do it. And then I want to plot out the function call. So right after that, right here, you will show the function call. We're here to do the same thing for conjugate gradient. And then function call plus 1 every time you substitute. For the line search, you substitute as well. And then show the function call when you display the error, display the iteration process. Now let's compare. Okay. Here, Newton's method, first iteration 6, second 12, and for steepest descent, actually 12 function calls. So every time is 12. For steepest descent, 12 as well, but only requires 3 iterations. So it seems like Newton is great, right? But when you have large problems, the Hessian is so large, the inverse of Hessian could be causing a lot of, occupying a lot of time. So people still try to avoid Hessian. You try that at home, you know it's terrible, right? So for simple problem like this, Newton is great. But for complex problems, people tend not to do Hessian. But if you use steepest descent, you realize this zigzagging is not effective. The conjugate gradient is great because it doesn't require you to compute Hessian and still have pretty good efficiency to find a solution. Even though it looks like you need more function calls per iteration, but when the Hessian is large, maybe you become more effective for the gradient. Okay, so maybe we can truly estimate how much function calls we need. Try to compare all these. Let me see. let's talk about the function calls. For Newton's method, you will be evaluating at this point, and for finite difference, you will be evaluating these points. This is the original place. This is like a del x1, negative del x1. This is like a del x2 and negative del x2, right? And this is plus delta on x1 and also plus x2. You are evaluating those points for multi-dimensional problems. So you will be evaluating 2 times your dimension plus a combination 2 pick up 2 times a plus 1. So what is 2 times d? For every dimension, you will be evaluating, you will be evaluating 1 step further and 1 step backward, right? 1 forward and 1 backward. That's 2 times right here. Every dimension you do that. And every 2 dimension you will check off diagonal term. So combination every 2, right? This is combination of d over 2. Choose 2 from d. So in Taiwanese, we don't write it down like this. We write down like this. So for Taiwanese, you know what is this? C D 取2, but that's for Taiwanese. No one writes this in the world. In the world, we write it down like this, right? But only Taiwanese, we say C D 取2, but this is a combination 2 out of D, right? And then you will also do function evaluation at the center. That's y plus 1. So for Newton's method, this is how much finite function evaluations you need to do per iteration. So multiplying the iteration number. And for steepest descent, you only do gradient. So it's like this is where you are. This is increment in the first dimension, increment on the second dimension. You don't need Hessian. So you are only doing d plus 1. Yeah, d plus 1. And multiplying the iteration number. This is only, also line search. For the line search, because you are doing, so you also need to plus the line search. For the line search, so you have to say d plus 1 plus whatever you need to do for the line search, and you are using 1D Newton. So 1D Newton, you need forward and backward, and also at the same point. So it's a forward and backward at the same point with your initial guess. So it's 3 points times the iteration number you need for the line search. I'm gonna say line iteration and say line search. This is what you need, and overall it depends on how many iterations you need. Okay. And how about conjugate gradient? Conjugate gradient. Similarly, for the first iteration, actually the same equation. Because you only evaluate the gradient and also do the line search. So what's the difference? So usually this is a large number here because steepest descent takes a long iteration, so I is large. And here I is much smaller. So conjugate gradient definitely a much more effective way when you compare with steepest descent. So can the function cos become more efficient than Newton's method? When d is large, maybe this number is smaller. So because you evaluate different things, so there's no proof whether the second equation is greater than the top one. But in some cases, in some problems, when you need to do so-called a CD, the combination of 2 out of d, then that number could be large. And when your problem is very nonlinear, maybe the Newton's method doesn't converge in 1 or 2 iterations. Then every iteration you need to compute so much, 2 times d. 2 times d is greater than d plus 1, right? And for the line search, sometimes it doesn't take that much. So from here you can kind of see how they are different. If you do have a quadratic problem, the dimension is not large, I would say use Newton, because you may not need a lot of computational time. But when you have maybe a very high dimensional problem, maybe try conjugate gradient. But the issue is conjugate gradient is more complex when you try to use it. I have a graduate student, I asked him to use this to solve a problem and asked him to do programming for this. It took him weeks and still have some bugs. Right? So the mathematics is a little complex right here. So if you are, if you fully understand what to do over here, it's actually not very difficult. If you check on my code, the differences are so minor. This is my conjugate gradient code. This is steepest descent, right? But in the steepest descent, I had this equation. We use this all the time. Negative alpha times the gradient. But for conjugate, one student helped me earlier, thank you. It's alpha times some direction. For the first iteration, the direction is negative gradient. Starting from the second iteration is negative gradient plus an update term. The update term is the norm of current gradient over norm of the previous gradient squared times the previous direction. If you know how to do this in computers, you can have really effective iteration process. You don't need Bayesian, and you can converge fast. This is supposed to be a pretty good method. Okay, so I really encourage you to use this method later on in the future. Okay, so that's it for today. I think we need to assign a homework. Okay, so homework for today. Solve the exam 1 by conjugate gradient. Okay, and it is supposed to converge pretty quick, maybe within 3 or 4 iterations. So just solve it to the end. You have the exam sheet, right? Just continue to work on that. You don't need to do the first iteration anymore because in your second problem of your take-home exam, you already did the steepest descent. So you can follow what you did last time and then start from the second iteration. Then starting from the second iteration, start to update the conjugate direction. You should be able to converge pretty fast. Okay? And you can check with you were doing a 3D problem. Right? That doesn't matter. You can do it. So you can compare with your solution from Newton's, because your Newton was supposed to give you the optimum. Okay? So I'm going to give you my code, but my code only run on 2D. I didn't expand it to 3D. If you want to modify my code, it's up to you. I'm going to give you my code for the exam as well, because for the makeup exam, I'm going to create a new problem, so it doesn't matter. Okay, I'm going to give you this exam code, and I'm going to give you all the codes I have today. I'm going to give you the notes and video. So next Monday, please hand in the homework. Solve the problem with conjugate gradient. And whoever wants to join the makeup exam, same time this Saturday from 9 to 9. Different problem. The area only, the exam only covers the Newton and steepest descent, not the conjugate. Okay? That's it for today. Thank you. Bye-bye. Is it a lot today?
Well,
It is a lot, I know. Later on, there is something called quadratic programming. That's the second time you will feel this terrible. Okay, that will be the only next time you feel this.